In the last video, section 4.2, we talked about getting the exact precise area beneath the curve using summations and a limit as n goes to infinity. It was pretty effective, and we did find ultimately that the area was indeed very close to our original approximation. But our original approximation was just that, an approximation. So the area we just got using the limit method gave us a much better answer. It's the exact answer. It is the exact and precise area beneath a curve. Now I want to show you that that method has its flaws, because somehow you got to take those sigmas and turn them into formulas, because there's no way that either you nor a computer could really run those sigmas manually. I could run manually sum I squared from 1 to 100. I could sit there and do 1 squared plus 2 squared plus 3 squared plus 4 squared, etc. I could certainly set a computer off to do that, and it would have it done just like that. But how do you sum I squared from 1 to infinity? Nobody can do that. Not you, not the computer. So we need to somehow translate that into a summation formula. And if a summation formula does not exist for a particular summation, then we're stuck, and we really can't go on. So what I'd like to do is demonstrate an example where it's breaking down a little bit. That summation formula method of finding the area isn't quite working, and then I'm going to give you a remedy for that, a way around it. So let's take a look at what are called Riemann sums. Now, Riemann sums are sums in which we add up the area beneath the curve by breaking it into intervals. And we've done this before. In fact, this is an interesting thing that we're going to do here, because I'll break this up into intervals, and for now we'll make them somewhat, they don't look equal, we'll make them equal though. Delta x, delta x, delta x. Okay? This function will be the square root of x. And we've been here before because we have just previously used this function, and we found that this area over here in the corner was 1/3. Therefore, this area, and this is 1, 1, this area here under the curve should be 2/3, because the overall area, the square here, is 1 by 1 is 1. So that's what I'm trying to figure out. Is the area beneath this curve from 0 to 1 truly the 2/3 that we would expect it to be? Well, right now, the only way that we know how to get the exact area under a curve is to use the limit method. We send n off to infinity. We add from 1 to n rectangles, the area of rectangles, f of x sub I multiplied by the delta x. So this is my height, this is my width. This says add them all together, and this says actually what I want is an infinite number of them, so that we avoid the approximation blockiness and we get the exact area. Let's try this. So A will be 0. B will be 1. We'll set those up here. And we do know the formula that we've used in the past. Delta x is b minus a over n. That would be 1 minus 0 over n, or just 1 over n. Not too difficult to get delta x. The little pointer, x sub I, that points to x1, x2, x3, etc., would be, you always start at A, and you add I delta x's to get to that specific x value. So A is 0, that makes it easy, and then I is I, and then delta x is 1 over n, so x sub I is I over n. So far, working out pretty well. So now, let's see if we can really figure this out by putting it into the function here and putting delta x over there. So the exact area should be, using this limit method, the limit as n approaches infinity, the sum from 1 to n, the f of x sub I, multiplied by just delta x. Remember, don't multiply these two together. Be careful of that. Okay, now, what's next? We keep copying the limit and the sigma until we're ready to simplify those using summation formulas and then ultimately maybe direct substitution. But wait, we have to execute our function. So getting delta x and x sub I, always important. Putting that into the function, important. But execute your function. Now, our function right now is the square root of x. So that's what it does to input. And that's what it'll do to my input. The square root of input, square root of x. Well, let's see. We get the limit as n approaches infinity of the square root of I over n square roots of n. Now remember that n's are considered constant for sigmas. Because I equals 1 to n, the I changes, the n does not really change until you run the limit on it. So you can bring these out front. I'm okay with those. And finally, we end up at our sigma. And then we're in a bit of trouble. I've hit a dead end. And the reason I've hit a dead end is because this is ultimately what you're supposed to do. The real problem is not only would I not want to do that manually, I don't want to sit there with a calculator and do square root of 1 plus square root of 2 plus square root of 3. The real problem is that I have to push n to infinity, so it's physically impossible to do this task manually. We have to have a summation formula to bail us out. But there is no summation formula. So I'm sorry to report, but we don't have one. We have a summation formula for summing constants. We have a summation formula for summing the letter I itself, 1 plus 2 plus 3, I squared or I cubed. There's probably even a good one for I to the 4th power and I to the 5th power, but no one's ever discovered one for the square root of I or the cube root of I or any irrational operation on I. That's it. Dead end. Well, we're going to play a little trickery here to get through this dead end. We're going to try our best to make it so that we don't get the square root of I. I want to put a better formulation for x sub I into my function. And I want you to think about that for a second. What do you think we should do here? So here was the problem. The problem was here. The square root of n doesn't bother me. That doesn't bother me in the least. It's this square root of I that bothers me right here. That's troubling, because that's going to be sitting behind a sigma, and we will not be able to do this. Any ideas as to what you might inject into the function to get you a better result? Something that will get you a nice I or I squared or a constant or something like that. Think about it for a second. I put an I in, I'm getting the square root of I out. Wouldn't you think it's a better idea to put an I squared in there? And that is a better idea. So what we're going to do, this used to be x sub I and it just didn't work. I'm going to abandon everything and make my own x sub I up. And if we're going to do I squared, might as well do n squared and make things incredibly clean. Okay? Now, what I like about this I squared over n squared concept for x sub I, which is the pointer, by the way, is that the f of that is I over n. And ultimately, we're going to do the summation of I, and that means I should be able to complete the problem. Now, the clincher here is, what's the side effect of picking that as my pointer? So we better investigate further and find out what is that going to do to this problem, because we've completely abandoned the old approach. So I just sort of came up with this idea, but what does this thing do as a pointer? Let's do an example. Let's make n equals 4. I want to know what x0 is. I want to know x1, x2, and x3, and x4. What are all these things? Let's see. x2 would be 4 over 16. x3 would be 9 over 16. x4 would be 4 squared, or 16 over 16. So, you know what? I'm still going from 0 to 1, so I didn't really violate the fact that we start at 0, we end at 1. That still worked. And here's what happened. It's still pointing to x values in between 0 and 1. It still starts at 0 and still ends at 1. But something did happen here. And here's what happened. So I still am going to go from 0 to 1. That's good news. But here's what happened. We break this up into halves. We break it up into quarters, eighths, and sixteenths. So where is x0? x0 is right here. Where is x1? x1 is right there. Where's x2? 1, 2, 3, 4 sixteenths, or a quarter. x2 is sitting right here. Where's x3? 1, 2, 3, 4, 5, 6, 7, 8, 9. That would be right here. x3 is here. And where's x4? x4 is right over there. So I want you to see what happened to our rectangles. Unfortunately, delta x is no longer constant. In fact, this is delta x1, this is delta x2, this is delta x3, and this is delta x4. The reality is that by choosing that particular formula for your pointer causes the delta x's to be different. Now, is that a bad thing? Like, will that prevent me from getting the exact area? I don't think it will, and here's why. So again, we're looking at the square root of x, and we're running it from 0 to 1. And the only difference is now I've basically broken this up in a different way. So what's going on here is that we are getting, and if we want to do an underestimate, we could do this. Okay? So there's no area on that first one. We get some area here and here. So by having a variable delta x, which is going to introduce a little more complexity into the problem, will that prevent you from still getting the exact area? And the answer is no. It'll still allow you to get the exact area, because ultimately, how many rectangles do you want in the problem? You want an infinite number of rectangles. So ultimately, where do all the delta x's go? All the delta x's must go to 0. And we're right back to that situation where you have those hair-thin rectangles all lined up under this curve, and there'll be no blockiness anymore. So we're still going to send n to infinity, which still sends all of the delta x's to 0. I realize as this problem evolves, some delta x's are bigger than others, but ultimately they must all go to 0. in order to fit an infinite number of rectangles. So, I need to come up with a formula for delta x sub I, because the new area formula looks like this. It's the limit as n goes to infinity. It's still a sigma, I equals 1 to n, but the problem is this. Not only do we need to evaluate the function at each x value with our pointer, our new pointer, but delta x is different every time. So it's not just our clean b minus a over n anymore. Each rectangle has its own height and its own width. So that definitely will make the problem a little more intense. Now, we chose x sub I to be I squared over n squared primarily because we thought it was a good idea, because the function will take the square root of that, and we'll have a sigma of I, which means I should be able to use my summation formula. So this was just an idea. This was the side effect. This is also the side effect, delta x sub I. So I think what we're going to have to do here is come up with a formula for delta x sub I. That's going to be important. So, let's say we do it from here. Okay? And we'll make this my I. This will be, we'll call this x sub I. And then we'll call this x sub, well, I minus 1, right? So delta x sub I could be this width right here. So we'll do it on just one of them. So what is delta x sub I? It's nothing more than x sub I minus the previous. Like that. X sub I minus x sub I minus 1. Like x sub, let's see, 1, 2, 3, x sub 3 minus x sub 2. Should get me delta x sub 3. So what's the formula for x sub I that we came up with? I squared over n squared. So what would the formula be for x sub I minus 1? I guess it's I minus 1 squared over n squared. N doesn't change. So what's the formula for delta x sub I for this specific problem? Let's find out. I squared minus 2i plus 1 all over n squared. Let's do the math in here, guys, because they share the same denominator. So I squared minus I squared plus 2i minus 1 all over n squared. Well, something nice happened here, and that is that these two cancel. So you see, I really had to do a whole lot more work to get delta x. In the previous examples, delta x was just b minus a over n, end of story. That's all I had to do. Here I actually started with x sub I, and it was just an idea. It was like, how can I make the summation formula work? I squared would make a good idea because I'm going to take the square root of it and I'll get my I. I will have a sum of I, which I have a formula for. Side effect was I got these variably width intervals here, or the rectangles were variably width, and therefore delta x was not constant. So again, how do you get delta x sub I? You just subtract the two x values here. Well, I have a formula for that one. It's I squared over n squared, and therefore the formula for the previous one would be I minus 1 squared over n squared. So I'm working this out, and I now have a formula for delta x sub I. It's 2i minus 1 over n squared. Now, let's piece this together. So apparently the area would be the limit as n approaches infinity of the sum from 1 to n of the f of x sub I times delta x sub I. I'm afraid they're both variable. Well, I think you're going to see in a moment that we chose well because we chose x sub I to be I squared over n squared. Just thought it was a good idea. It still covers the entire interval from 0 to 1. I did prove that. And I just came up with a formula for delta x sub I. It has an I in it. So now, this strange variably width set of rectangles We've got our delta x sub I for each one. We have our x sub I for each one. And you know what we got to do next, guys? Execute the function. Remember the function? It was a square root function. Apparently, we chose x sub I well, because now I have the limit as n approaches infinity, the sum from 1 to n of just I over n, but this is delta x sub I over here. And now we do the algebra over here. So we get the limit as n approaches infinity. We get the sigma I equals 1 to n. How about we work this out? 2i squared minus I all over n cubed. You'll notice that when we get to this stage, there are no x's, there are no delta x's, there are no sigmas. Oh, wait, there is a sigma, sorry. But there are no x's anymore, and basically it's i's and n's. So I'm looking for patterns. I'm looking for the sum of I. I'm looking for the sum of I squared to resolve this problem. So it's the limit as n goes to infinity. Remember, each one gets their own sigma. So the 2 comes out front, the n cubed comes out front, and we get a lone sigma of I squared. We have a formula for that. Minus the 1 over n cubed comes out front, and we have a sigma from I equals 1 to n of just a lone I. This is something we can do. So I need to imagine this strange movie that's happening right now, and that is we started with those variable widths for each rectangle, and then I'm going to push n to infinity. So the small ones get smaller, the big ones get smaller, and as they get smaller, they all sort of pile together, and ultimately they all must go to 0 because n is going to infinity. The only way to fit an infinite number of things is to have each one of them thin, basically 0, so that they can all line up next to each other. So even though they were variable, it still didn't matter. They all went to 0, and now we have these hair-thin lines that used to be rectangles that line up and sweep under that curve and give me the exact area. Well, luckily we have formulas for this. You know the formula for the sum of I squared. It's n plus 1, 2n plus 1 over 6. We have formulas for this. And that one is n plus 1 over 2. It's a slightly easier formula. And we can cancel this n with one of these down here. I can cancel this n with one of those down there. And let's see what we have. 2 over 6 is a third. So I'll put that out front. And I always seem to have to multiply this together, this FOIL action here. So this is 2n squared, 3n plus 1, all over n squared. Over here, I have, let's see, 1/2. Bring that out front. And it looks like I've got n plus 1 over n squared. Let's give each one their own copy of the denominators here. So this will be the limit as n goes to infinity. We have 1/3 times 2n squared over n squared is 2. 3n over n squared is 3 over n, and then 1 over n squared. Over here I have a half. I have 1 over n and 1 over n squared. I don't think that's going to contribute to the answer because we're going to send n to infinity in all cases. These will shoot off to 0. Finite over infinite is 0. So look what we got. And that matches my expectation level on this problem. So while in the previous video I actually made a mistake, I forgot to multiply something through, I realized the mistake because the answer didn't match what you expected it to match. In this case, my expectation was that we actually did the area up against the y-axis on this very curve earlier, and we discovered that that area was 1/3. Now I know that the area of the full rectangle is a 1 by 1, which is 1, so 1 minus 1/3 is 2/3. It should have been 2/3. So that's called the Riemann sum. There's no question that that is much more challenging than just doing a regular summation problem. So for the most part, I think a Riemann sum is something that would be reserved for a take-home assignment or something. I wouldn't give that to you on an exam necessarily. I would give you a regular delta x constant version of the problem. So make sure you can still do that. Delta x equals b minus a over n. X sub I is a plus I delta x, and then run that through. So now, it's an intriguing way of getting there and sort of cheating our way there by making that function produce the I, and we got the sum of I, because when it produced the square root of I, we were lost. The side effect was these variable widths. It's not that I wanted variable widths. That was actually a side effect, but the side effect didn't really cause me any problems, because ultimately by making n go to infinity, all the big ones and the small ones all collapse down to 0, and they all fit next to each other anyway. So we still get the same result, which is the exact area. Okay. Now I want to finish up with the other half of this chapter, which has to do with definite integrals. And I think we'll do that in another video. And that's where we do a definite integral using the integral symbol. And instead of just doing the antiderivative, we actually put limits of integration. We put the a and b on the top and bottom of the integration symbol, and it has new meaning. It's called the definite integral. And a definite integral will give us the exact area underneath the curve. Now, for now, we're not going to do much calculus on it. We're going to just talk mostly about the terminology and the properties. So tune into the next video to see that.